So in this lecture, we're going to be talking about synthetic controls, which is a method of causal inference that has become very, very popular over the last couple of years. And you can probably see within a couple of slides why this is the case. So synthetic control is related to difference in differences, but it deals with a particular problem, namely that in a difference in difference estimator, we always need a large number, or at least a significant number of units that have been treated and others that have not been treated. It's very hard to estimate a diff in diff and to draw any meaningful inference when only one unit has been treated. Yet we have many cases where we actually like to analyze what the causal effect is of a policy change or of some event that happens, but we only have one unit that has been treated. Okay, so here on this slide you can see some examples for that. Some countries may suffer from a conflict, or there may be some agricultural shocks that only happen in that one country and nowhere else. Or if you think about any macro policies, such as changes in fiscal or monetary policy, they affect everyone in the same country, and you may not observe many other countries that had similar policy changes, so you can't estimate a diff in diff. But what we can do instead is we can use the synthetic control method to do exactly, to get a causal estimate of the effect of such policy changes. Okay, so the challenge, again, for any causal inference method is how do we find a suitable counterfactual, and then in addition to that, when it comes to synthetic controls, because only one unit is treated, inference is also a lot more challenging because we can't use the conventional techniques of calculating standard errors how we would do it with any other method. The key ingredient to synthetic controls is the counterfactual that is constructed, and unlike in all the other methods that we've talked about, where the counterfactual is constructed based on the notion of a control group that where we make a good argument why that control group has not been treated and is a suitable control group, here we actually look at a data-driven counterfactual. Okay, so we let an algorithm choose the counterfactual. So that's obviously very, very different from the other methods. And on the one hand, this is the reason why synthetic controls has become such a powerful tool, because we can, for almost any policy change, we can evaluate the effect of that policy change by letting an algorithm find a suitable counterfactual. But that advantage also has triggered quite some criticism because obviously sometimes the counterfactual that is chosen by the algorithm may not be the most sensible one. Okay, so if you think, for example, about a policy change that happens in Ireland, and you let an algorithm choose counterfactuals for what would have happened in Ireland had it not been for that policy change, the algorithm would not necessarily choose countries that are similar to Ireland, but would simply choose, may choose countries in very different parts of the world that are very, very, very different in many ways. So it's, in that sense, it's an atheoretical method, and we always have to be careful when using it. It's extremely simple to use. I will show you that in this part and the next part of the lecture. But you have to be aware that there are that there are justifiable criticisms of that method. So the idea here is that we get this data-driven counterfactual by choosing, first of all, a large number of potential control units. So if we look at the change in one country, then we have a lot of other countries that would be potential control units. And what the counterfactual is a weighted average of the outcomes of all those control units. And these weights are chosen by the algorithm such that the trend in the outcome before the event is matched in the best possible way. Now, I'll show you an example to illustrate what I mean by that. And this is actually the first well-known paper using the synthetic control method. So Alberto Abadi from MIT is probably the person who made this method really popular, and who I'm not sure if he was the person who developed it, but he was definitely the person who developed a lot of tools related to synthetic controls. And so this is the classic example for synthetic controls. So what they wanted to study was the effect of terrorism in the Basque Country in Spain on GDP. And it's a classic case. Thankfully, there was only ETA terrorism in one region in Spain and not in the others. But that means we can't easily estimate a diff in diff because we only have one unit that was treated for some of the time. So what they do instead is they use the synthetic control method and try to see, can they find a weighted average of all the other Spanish regions such as to match the pre-trends before the actual start of that terrorism episode as best as possible. And so you can see here that the terror started in around 1975, and that graph is the main graph in that publication, in that AER paper. And obviously, I'll walk you through in the next couple of slides in how to get to that graph. But this is just to get the idea across what a synthetic control does. So what you see here, that the solid line is the GDP of the Basque Country. And what the dashed line is the synthetic control, as in that's the counterfactual of what would have happened to GDP in the Basque Country had it not been for that terrorism. And you can see that what they do is through the algorithm, they manage to match here in the pre-period the actual trend in GDP very, very well. And everything that follows then is to just take the weighted average of to take those weights that that the algorithm has chosen in order to match the pre-trends, and also apply those weights to the post period, so to that period. Now, the assumption that is behind this is the same as with diff in diff, namely that of parallel trends, that in absence of the treatment, the treated and control groups would have moved in the same way. So that in absence of the treatment, the trajectory of the Basque Country would actually have been this dashed line here. So how is this done in practice, or what's behind this? So we have to start with a bit of notation and a bit of lingo. So what we observe is J+1 units. So in the case of Spain, this would be the Basque Country would be the 1 unit, and then all the other Spanish regions would be the J units. and we observe each of these units in multiple periods. So without that time dimension, a synthetic control study would not really make sense. Then it would simply be a matching study, but we do not have that nice feature that we can actually match pre-trends and simply inspect how good a job we do in constructing a counterfactual. You can't do this when you just have a cross-sectional matching, as you would have learned it in Econometrics 1. So the idea here is that one unit is exposed to the intervention in time t equals tau and is treated in all periods after tau. So there is surely going to come the method soon where units are allowed to switch into and out of treatment, but that, of course, is a lot harder to conceptualize. So for the moment, most studies we will consider and most applications of synthetic controls, they assume and they study settings where a unit is treated and then remains treated thereafter. And so these J units that have not been treated are part of what's called the donor pool. And one conceptual issue here is that they should be untreated. So it also means there should not be any spillovers possible. And that depends again on your context, on the context of your study. So if you want to look at, let's say, the effect of something that happened in Dublin and use other Irish counties as control counties, as the donor pool, that's probably not going to work very well, because if there's a large shock in Dublin, it will obviously transmit very quickly to other places. So in that sense, it is a partial equilibrium concept, and you have to you can only apply to settings where you can conceivably exclude large spillover effects, because obviously those spillovers would in turn affect the counterfactual, and you want a pure counterfactual that is not contaminated by spillovers. So then we have the potential outcomes now in treated and control units. So those with a superscript 0, those are the ones in the donor pool, and those with superscript 1 are those in the treated unit. And then we observe them obviously in several time periods. So what we want to estimate that is a simple treatment effect, and we can think of this as estimating separate treatment effects for each time period after the treatment, or we can also think about an average treatment effect for all the time periods after the treatment that we are interested in. Okay, so if we want to, for example, say, well, how much GDP per capita did the Basque Country lose out on because of terrorism, we can also obviously sum those treatment effects up. So in that case, it would make perfect sense to do so. Okay, so the treatment effect is very simple. For a given time period t, the treatment effect would be simply the actual outcome of the treated group, or in that case just the treated unit, minus the synthetic control, so the weighted average of all the units in the donor pool in the same time period. Now this counterfactual, as I mentioned, is a weighted average. So you have here the actual outcomes of all units or of each unit in the donor pool, and then each unit gets a weight W star. And these weights, they have to be obviously between 0 and 1, and they have to be greater than 0, at least, or greater or equal 0. Okay, so you will see in practical applications that very often a lot of units in the donor pool will get 0 weight, and then a heavy weight rests on a handful of units. And the question is, well, where do those weights come from? And when it comes to synthetic controls, and actually also when it comes to any matching procedure, these weights are determined by an algorithm in an optimization procedure. So one important thing to note here, obviously, is that if you have a different weight vector for all those units in your donor pool, you would obviously also then get a different synthetic control. And so it also then depends on what units you include in your donor pool to be considered in the first place. They will then determine the weights that the algorithm chooses, and they will then determine also what the counterfactual outcome would be in the end. So the idea here of how these weights are being found is as follows. So we take characteristics of the treated unit. So this is what's denoted by the vector x1, and these can be characteristics that are static, but these can also be pre-treatment outcomes, or these can be time varying characteristics. So you don't need to purely rely on pre-treatment outcomes. So in the case of the Basque Country, this would be GDP, but you can also think about other economic variables that you want to match. And so we take that set of variables for the treated unit and then take the same variables for the control unit, or for every unit in the donor pool, apologies. And so the goal is then to find a vector of weights that minimizes the distance between those two sets of characteristics. And so for that, we need actually two sets of weights. So the one set of weights, W, is the set of weights that determines how much each unit in the donor pool counts within the counterfactual. Okay, so in again the example of Spain, how much does Catalonia and how much does the region around Madrid, or how much does Galicia count for the synthetic counterfactual? But that's not the only dimension that we're looking at here, because what we can also consider is that for each unit we observe multiple variables. Okay? So the idea is that you observe, for example, their pre-treatment outcomes in multiple time periods, and you observe different variables. So you can, for example, match based on unemployment rates, or based on population sizes, internal migration, whatever variable you think is a useful variable to match on. And so so each of those variables obviously also needs a weight to go into the counterfactual, or that governs how important that variable is within the synthetic counterfactual. So that's V. So here is how this procedure works in practice. So we want to minimize the distance between the target variables, that's x1, for the treated group, and the same for the counterfactual. Okay, and so that we simply do by minimizing the square root of the squared weighted difference between those two. Okay, so that's what's shown here. What that expression under the square root is. So once again, you have here weights for each unit in the donor pool. How important is that? That's W. That's here and here, and you have for each unit you observe multiple variables. So each year variable combination would be counted as a separate variable, and then each additional variable each static variable that you throw in there, population size or something like that, could also would also be counted as a separate variable, and so that that would be governed by those weights V. Okay, so, but otherwise, it's a standard, or it is a standard minimization procedure, and there are algorithms that can easily solve this. And so that's what's behind synthetic controls. Again, depending on what algorithm is being used, that of course, that determines what counterfactual you will typically get. This sounds all pretty arbitrary, so it sounds as if different algorithms would yield very, very different counterfactuals and different results. In practice, this seems not to be the case. So the simple minimization algorithm, so it's just a method of moment procedure, does typically a very good job at finding a counterfactual that matches the pre-trends very, very well. It actually matches in most cases the pre-trends to such a so tightly that some people have expressed doubts that it's actually useful. It almost looks like it's too good to be true. Now, one of the main people, besides Alberto Abadie and Guido Imbens, working on synthetic controls, is Jens Heinmüller from Stanford. He's a political scientist, and he has developed packages for Stata, MATLAB, and R. And in fact, he has a video on his website where he shows how to implement synthetic controls within 10 minutes to get basically all the important graphs and tables, and it's actually really easy to use. Now, there are refinements to synthetic controls that I will talk about, or that I will at least give you the references in lectures in the second part of this lecture. But ultimately, as any causal inference method, it always follows the same protocol, and then you have to obviously, whenever you run such a study, see, does it fit your context? Does the method fit your context? And can you also, or do you need any methodological refinements such that it fits your context? So back to the Abadie and Gadiazabal study in the AER. So again, here the idea was you had this terrorism episode in the Basque Country starting in 1975. The question is, what did this do to GDP? And they used synthetic controls whereby all other Spanish regions are in the donor pool. And here, this table shows why why it would be very hard to just do a comparison of the Basque Country before and after relative to the rest of Spain before and after. So basically a 2x2 diff in diff, which would be the simplest way of doing this. The reason we can see here is that Spain on average is a lot poorer, for example, than the Basque Country. Okay, so if you see, the Basque Country has a much higher population density than Spain. Its share of people working in industry is a lot higher, and you also have a higher educational attainment on average. So that all means that the average region in Spain is not a very good counterfactual for the Basque Country that actually had a much higher GDP and was doing better relative to or in many measures. So what they do then is they run the synthetic control and simply get the algorithm to find weights based on a couple of variables. So they use several GDP values from years prior to 1975, as well as other variables such as the share of people with at least a primary education or the share of workers working in industry. And when they do that, what comes out is that the synthetic control for the Basque Country, the weight only rests on 2 out of I don't know how many Spanish regions. So Catalonia gets 85% of the weight, Madrid gets the remaining roughly 15%, and that's it. So all the other regions, and not by the researcher's choice, but by the choice of the algorithm, get a weight of 0. And what we can see here when we compare then the actual Basque Country to the synthetic Basque Country is that it matches it pretty well. Okay, so not only did we see in the previous picture that the pre-trend is matched, but, and this is something that a good synthetic control study should do, we also see that it matches other characteristics pretty well. And that is simply more reassuring than just looking at pre-trends, because we can always find control units with similar pre-trends, but these units would be so different in other ways that it's hard to argue why they would be a suitable counterfactual in the first place. Okay, but here, at least, this gives us a bit of an idea that or gives us a hint of as to whether the counterfactual is a sensible one or not, right? And so you can see here that in terms of literacy rates, it doesn't do a perfect job, but it's definitely closer. The synthetic control is definitely closer to the actual treated unit. And you can see in terms of GDP, it hits it pretty well. In terms of population density, it's also a lot closer, and so on. And so they then use the weights. And again, the weights have been determined in the pre-period, so in this period here. And then they simply use the weights to trace out that dashed line here. That's the way synthetic controls works. And then what they do is for every year thereafter, or for the entire period, they can then calculate the treatment effect as the difference between treatment and control. So that part of synthetic controls is very simple. And in general, to apply this method is actually a very, very simple one. I can even sometimes give this to undergrad students as a project, and I show them that video of Heinmüller. And obviously, I'm not asking them to do all the the methodological, or to apply all the methodological refinements that you would need to consider for a publishable paper, but they're typically able to produce this graph, and that is oftentimes, with any paper, if you have a very good graph, is half the battle in making a convincing case. Okay, so what this shows is basically something like the first stage. So what they graph here is, on the one hand, the dashed line is the GDP gap. So it's the gap between the synthetic control and the actual GDP in the Basque Country around that time. And you can see that it goes down around the time in the late 70s. So that's exactly when that gap here on that slide opens up, and then it remains fairly constant. And you can see also that this is the time when there was this uptick in the cases of, in the number of people who died from terrorism. Now, the big question for any causal inference method is, well, what about unobservable factors? Okay, it's an observational study. We don't have proper randomization, so unobservable factors will surely play a role. Okay, so and we have to make, as with diff in diff, we have to make the common trends assumption. And as in any study, you have to argue why the parallel trends assumption would hold. So you have to argue why there is no spillover effects. You have to argue why the control units that were chosen by the algorithm, they make sense, and why it's not just some random control units that were chosen that match the trend well, but we can have very little confidence that afterwards, after the unit has been treated, that it actually represents a sensible counterfactual. So this is obviously less of an issue when you have a very long pre-treatment period, because obviously the longer your pre-treatment period is, the harder it is to find a good match with units that are very, very different from your treated unit. I'm not saying impossible, but it's just harder. And also, it's obviously it's obviously unobserved factors are less of a concern when you match on actual pre-treatment outcomes. So in the example of Spain, when pre-treatment GDP is actually part of your matching algorithm. And this is just from a practical perspective, I have hardly ever seen a synthetic control study whereby researchers would only match the pre-trends and would match the pre-trends well based on variables other than pre-treatment outcomes. You typically get the good match when you match in part on pre-treatment outcomes. Now, a big challenge for synthetic controls is statistical inference. So we already talked about this in Econometrics 1, I believe, that inference in diff studies where a number of, for example, states are being treated, even their statistical inference is very, very hard, and conventional standard errors massively underestimate the uncertainty that is in any econometric model. And the reason for that is that you have serial correlation in the outcomes of each unit, and conventional standard errors obviously don't take this into account. So you would have to cluster at the level of units, and that approximately gives you the right standard errors. That's what Bertrand, Duflo, and Muller-Nathan have shown in that QJE paper over a decade ago. So that's for diff in diff. But there at least you have typically a lot of treated units. And so if you have, let's say, 50 states and 10 of them have been treated, you cluster at the state level, you have 50 clusters. So, asymptotically, your standard errors should be all right. Okay? So you don't have this problem of too few clusters, just about that you don't have that. With synthetic controls, that's very different, because all you have ultimately are 2 times t observations, right? So you have t periods. So that's the entire sample period from the first point before the treatment to the last point after the unit has been treated. And you have this for the treated group and for your synthetic control, but that's it. So these are 2 time series. So you have extremely high serial correlation. That's what time series are. They're not independently drawn observations. And at the same time, you only have 2 clusters. So conventional inference just does not work, right? There is no reasonable assumption we can make about the error terms in the population that would then allow us to calculate some parametric standard errors, which is what we usually do, and what any standard errors that you get from statistical software are based on. They're based on parametric assumptions about how the error terms are distributed in the population. Here, we can assume whatever we want. We cannot get any meaningful parametric standard errors, which is why, and this is what I'm going to show you in part 2 of this lecture, we have to resort to non-parametric methods. So just to foreshadow this, the way this works is that we run placebo synthetic controls for every unit in the donor pool. So the idea is that we have, let's say, the Basque country treated, so that's our treatment unit, and we have however many other Spanish regions in the donor pool, and let's say these are 30. And what we would do is we would exclude the Basque country from our data set, and then run separate synthetic controls 30 times, and each time we choose a different region as the placebo-treated region. So we say, okay, now Catalonia is treated in 1975 and thereafter, and then let the algorithm choose an appropriate counterfactual for Catalonia, and calculate what the treatment effect would be. And we do this in turn for each region, to have each region once as the treated unit, and then find synthetic controls. And then what we can do is we can basically compare the estimate with the true treatment to all those placebo estimates. So it's a permutation based test. How this is being done, I will show based on an example in the next part of the lecture.